Gdje si, Tatjana? Sam nas dvoje.
Hi.
Bog.
Jesi ti siguran da smo mi na dobrom linku?
Šta ti je sa glasom?
Pa nisi skužio još jučer, nemam glasa više.
Pa nešta, ali tiho si mi pričala, znaš, jučer, pa nisam...
Ne mogu pričati.
Svašta. Valjda te neće prozvat danas.
I odšla kući. Došla kući, čovječe, i nema ni A ni B. Djeca se smiju sa mnom. Kuš koliki lončić pijem ovog čaja.
Dobro, ja isto svako jutro čaj popijem, ali vidim...
Hektolitar čaja imam.
Vidim, bome je velika.
Od litre. Kuš,
Dobra si.
ne mogu progovoriti. Ko zaklinac, kao ono, dosadno mi u životu. Joj, Bože.
Aj.
Pásate ya. Siempre te oyo la intro esta. Y te muteo. Hello guys and girls, good morning. How are you? Good? More or less? Okay. Wait, it's recording, yeah. Okay, so this week is embedded programming. We're going to start programming our microcontrollers. And today we have Guillem here, and he's going to give us a presentation about how to make a computer and an introduction to electronics in general, but in a more like a broad sense. Just to make sense a little bit of what these 2 days, today and tomorrow, are going to be. Guillem is going to make this overall presentation about digital electronics right now. Then I'm going to take over, and we're going to talk a little bit about algorithms and some bits of Arduino programming. And we're going to leave it there for today. Tomorrow morning, then we're going to go a little bit deeper into all these concepts, and we're going to understand what Arduino means in all senses. What is the Arduino framework? Where does it come from? And how can we build the same programs we write with Arduino, but without the Arduino abstraction? We will be talking about some more advanced concepts, but that are very helpful, especially for Thought Academy. And of course, MDEF students, if you want to come, you are more than welcome, as always. And this is, okay? So today, I leave you with Guillem, and hope you have fun.
So, I don't mind if you use this or this. So, if I talk like this, you listen to me well? Yeah? Okay, so I'll try to make it like this, and if you don't listen to me well, let me know. I'll switch the microphone. But you know, listening your voice so loud makes your teeth different, no? It's like you, let's say I feel less connected to you, right? So, and I guess the ones there, you see me well, perfect, yes. I'll just move this maybe.
No, I can move the camera.
Okay, that's it, perfect, yeah. Okay, so why I'm giving that talk today, or session with you, it's because we found out that actually, if you start to learn about Arduino, and especially in the way that it's taught at the Fab Academy, where you are not just looking at how to use it to interface systems. You are not just, let's say, learning how to use it for the end purpose of having, let's say, a computer controlling an LED or a motor. You're also learning the fundamentals, because you'll go down to writing code in C++, flashing microcontrollers, etc. So learning all these things with the understanding of basics of, okay, why are we doing it that way? Why let's say a computer is needed to work that way was a bit, let's say, I would say, unengaging. It was hard to engage if I just start to explain to you that, yes, you need to use C++ and you need to use GCC, and then you need to flash the microcontroller using an in-circuit serial programmer. It looks like, well, that doesn't make any sense. So the idea of these next 45 minutes, an hour, is to talk about those things a bit. So I call the presentation "How to Make a Computer." And so let's forget about everything we know about computers, for a moment. And let's see, sorry, this works, doesn't it? Yes. So let's forget for a moment about everything that we know about computers. And let's imagine, we are back on the 1920s, 1930s. That picture is from the Colossus computer, 1944-45, okay? And so let's put ourselves in the minds of the people on that time, because actually we take for granted many things around computing, which are just conventions, Let's say we agreed on making it one way because it was a way that we found it cheaper, we found it faster, we agreed on the industry that had potential to growth, but at the end, everything is about decisions. So that's why today we're talking about computing and not computers, right? Because when you talk about computers, you could get confused and you could suddenly say that that's a computer, but Arduino is not a computer. Let's talk about computing in general. So first of all, you might already know about this, but let's understand. Computers, of course, are much more than laptops and than servers, right? A computer, it's anything in a way that can use information to transform information, right? And so we can think on a computer as, at the end, anything. And today we'll look particularly about how a digital programmable computer works, which is a way to say how what nowadays we call a computer works. So to start about this, we need to think that computers are not silicon or binary, that we choose them because they are convenient. And that sentence might sound a bit like, oh, binary and silicon, what this is about? So let's kind of try to look at that. So first of all, right, if we start thinking about computers are not silicon or binary, so keep in mind, right, if we start from the fundamentals of why we use binary, we'll talk more about this later, but we use binary in computers, we represent things with ones and zeros and not, let's say, with a decimal system like the humans do, because it's much easier for a machine to deal with just two states, right, which is electricity or no electricity, than having to deal with 5 or 10 different states, For us, it's the opposite, because we have, let's say, 5 fingers here, 5 fingers here, so it's pretty convenient to count until 10, right? When you are a kid and you don't know actually how to count that properly, you use your fingers a lot. And I'm not an expert on anthropology or, let's say, history of humanity, but for sure, for many years and centuries, humans must be counting much more with the fingers than we do now, actually, So it makes sense for us. So a computer, instead of having, let's say, 10 fingers, it just has 2 fingers, because the fingers the computer uses, it's voltage or no voltage. It could be 0, 5 volts, it could be minus 15 volts plus 15 volts, it could be 0 to 120 volts, doesn't matter. Usually, if you think the ones on your laptop might be maybe 1.8 volts or 3.3 volts or even 5 volts, depending on the subsystem. And there's something called level shifter that will basically say, in this part of the computer, the logic of 1, it's 1.8 volts, but at the end, we don't need to know about this at the moment, right? But it's important, right? We choose that way because it's convenient. And of course, you might say, yeah, Guillem, but if I have something binary, which is just yes or no, how can I actually count until 10? And that's completely possible. It's basically us as humans that as we invented the numbers and we invented them based on the decimal system, based on 10 basic digits, after 10, you repeat the system, it works on that way. That we take, let's say, we just think that that's the only way to actually count. you can count on any base. There are systems that count at base 6, at base 16, and systems that count at what we call base 2, which is just 1 or 0 or yes or no. And actually, I don't want to give a big lesson of binary, but there's many tutorials and many things online. But if you think, it's actually just about asking questions, right? Let's say 0, it's that, no. And if it's a 0, it's a 1. So I say, yeah, it's a 1. It's a 0. It's a 1, it's a 0. So I can just count 0, 1, 0, 1. At the point I want to count until 2, no, I could say, okay, I'll use 2 bytes, no. And in these 2 bits here, I'll say, no, I'll say, look, that's 0, 1, no. And now I could go and basically add this one here and say the 2, no. And I could say the 3, and I keep counting. So it's you could find tutorials if you are willing how to count in binary, but just keep in mind, maybe as an assumption now, with yes or no, you could count until any number. And the other one is silicon, right? We'll talk more about silicon, but actually the idea that we can perform these operations in top of transistors and that we make transistors out of silicon, well, it's because we came out that was a good way to manage electricity, no? Even maybe a way that we decide to use electricity, because you could make a computer powered with water, for example, no? Or a computer powered with gears, actually. Let's think of a clock, right? A clock is a kind of a computer. It's not full purpose, no? You cannot compute everything. You just limit to do things with time. You could actually go at a clock and in a way reprogram it, because you could change now when it's the time it is, no? And it's everything based on gears, if you think on an old clock from 100 or 50 years ago, right? So there's many things about thinking about computing. So, and computers, they don't even need to be digital. Actually, the clock that we were discussing now, like a clock with gears, no? Like the clock maybe that you had as a kid, or that you still have now, or that your grandpa, for sure, or grandma had one. Those computers were actually not even digital. What digital means? Because that's the question, is like, what digital means? Well, we use digital in a way to define what means discrete, which is like, okay, and what discrete is. So discrete, basically, it means that you get something that's, it's infinite, something that actually it's continuous, and you make it into something that's continuous. And you'll say, okay, wait a second, what do you mean? Yes, look, if we measure that table, right? That table, I get a tape and I measure it, right? It might be, I don't know, like it might be, what it is, like it's 4 meters more or less, right? So, but it's not exactly 4 meters, right? I could measure and say, no, it's 4 meters and 10 centimeters. I could say, no, it's 4 meters, 10 centimeters, and 2 millimeters. But you actually see this table, it's not even that. It's not exactly that. I could keep zooming in with a microscope, no, and I'll find, no, that this value actually changed, no? And I need to go to microns and nanometers, no, down to that. So when we use digital system, it means that we get a fixed scale. So if our computer doesn't need to be that accurate, I will say I count in meters. And so this desk will be 4 meters. And it could just be 3, 4, or 5 meters, okay? The point about this actually is that once you actually make information discrete, actually it's much more easier to compute, no? I could deal with it, no? Because it's not like some infinite, a number there. It's actually a finite solution. Of course, you'll say, oh, Guillem, but you lose a lot of resolution. That's not good, No, you could make, instead of working in meters, say that my computer works in tenth of, let's say, millimeters. And suddenly, you get on a scale which is useful for your purpose. And you are familiar with it. If you actually use any software, one of the first things that asks you, software for modeling, is the resolution you want to work. If you open Rhino, it says, what template do you want, right? Because for the computer, it's super important to know how much actual information it uses to store, and that depends on the scale. So this idea of making things constrained to one scale, and a scale that's finite, to make it, let's say, easy, it's super important. Because even think on that, if I get this table here, and actually, I know you tell me, Guillem, I'll ship you desk. I'll tell you, look, you tell me, Guillem, you'll need to make desks for me. I'm going to tell you how long I want them, and I will just use meters. Well, if suddenly you tell me that something is 3.2, I won't care about this. I'll just make it 3, 4, or 5, right? No, I'll make it in meters. And that then might sound stupid. It's actually super positive. Because if you send me information and I don't listen to you well, you call me on the phone, it's like, did he say 3.5? Or he say 4 point, It's like, no, it could just be 3 or 4, right? So these ideas that might seem a little bit stupid actually are the fundamentals of, for example, how you perform error correction on a system. And so how you actually design a system that, despite there's noise around, it knows how to correct itself. So at the end, learning the principles help us to be creative. And that's why I'm talking about this here too. Not because you need to be computer scientists, but just so you get a bit of these ideas. And so there's this kind of, let's say, 4 concepts. Actually, we talked about them already. Analog versus digital, right? No? I can, let's say, we use centimeters and measurements for that, but think for a moment in sound, right? Sound actually, it's me moving the air on that space. When I turn sound into an MP3 file and upload it to Spotify, what I do actually know is that these things which they don't have units, right? Nature doesn't work with units, no? Suddenly it says this in a particular amount of units, and will say that it basically defines a resolution where this information will be encoded, no? And that's how I transform something which is analog into something that's digital. I'll show you more examples. Electronical versus electromechanical. Well, the first computers, they were mechanical. And then there were computers that were electromechanical. What does it mean? Well, it means basically that if you have a computer which is mechanical, instead of moving electricity, you might be moving levers, or you might be moving water, and maybe, a certain flow of water will mean a 1, a certain one will mean a 0, or maybe you don't have a computer which, if it works on water, maybe you don't even make it digital, you make it analog. So to represent a value, what you put is more or less water, so there's different ways of approaching that. In electromechanical computers, it's like, okay, I had my mechanical computer working with levers, and suddenly I'll use something more like relays, with wires, which there's electricity, but there's mechanical parts that move. And if I move 1 step forward, I will use it fully electronical. And think of this that now we take for granted was a big revolution, right? On the, let's say, 1910s, 1920s, when they got actually to use the first valve, properly, and they were able to start building radios, actually, this was a big revolution because imagine it's a machine that you open and there's no moving parts. Now that thing itself was revolutionary for the time. It's like, it's something that makes something, because actually a phonograph, for example, or a turntable, it spins, so you see something going there. You open a radio, there's nothing moving there, And from the valve that were big and consume electricity went to transistors, super small, And the idea here is that actually we make them even smaller, we make them actually consume less power, and they don't move, Which is like quite like, okay, it's weird for us in a way, And also there's an interesting idea here that we forget many times. The computer at the end, if it has a father, it's a radio. Like say the radio was something as cool and as magical as the computers were, or at least 20 years ago, and still are now, which is something that we forget sometimes. We talk about binary versus decimal. We talk about, actually, I could count in base 10, but it's easier for my transistors and my valve previously, and even for my relays, if I think on a computer built even before, to actually count using yes or no. And the last bit, general versus a special purpose, right? So a computer, we take for granted nowadays that a computer is always a general purpose computer. That's actually not true. So what does it mean? Because that's actually, that's the bit that makes the computer revolutionary. Because to make a machine that can just decode a particular kind of information, and it's embedded into the system how it does it, it's quite more basic actually than making a general purpose computer. So for example, let's think on, for example, an analog, electromechanical, not even binary or decimal, we'll call it different, a special purpose computer. Well, you know, that could be the key that opens your lock at home, no? It's kind of a computer that's capable of deciphering your key that has a shape like this, no? I don't know if you see, no? And it's capable of moving some pins, and if the pins are correct, it allows you to turn, no, the key. Well, that's kind of a really primitive mechanical computer that's not general purpose, it's a specific purpose. It's programmed to read a specific kind of key and just to perform one option, which is to unlock. So from this idea that it's quite old, now we went to where we are now, you know, which is actually on thinking that we have computers which are digital, electronical, they work in binary, they're general purpose computers. So that's how you will call an Arduino, that's how you will call your laptop, that's how you will call, let's say, any of thing that actually you usually call a computer. But there's other ways of doing it. That's what I want to show you. Going back to the bit of general purpose versus specific purpose, there's actually a lot, and they are super useful and super used: digital, electronical, binary, and specific purpose computers. Which are those? Well, let's think of them. For example, inside here, there must be a small chip, right? That's actually emitting light and counting the light differences and sending USB signals. That computer here, I cannot reprogram it to make something else. Why? Because it's too expensive to make a computer reprogrammable. It's pointless for that. They sell millions of mouses, so it makes sense for them to design something which is made out of silicon, it's digital, it's electronical, so it works on binary, but that's a specific purpose, no? It's something they put here, and it just has that function. You cannot reprogram it. And the world is full of them. If you think, for example, of your laptop, even, for example, quite a common, a specific purpose computer. It's the graphic card on your computer. The graphic card of your computer, it's digital, electronical, it's binary, and it's quite a specific purpose. I mean, you could program it, actually, right? But it's not meant to compute everything. That's kind of not true right now, because the truth is that in the last years, we found out that GPUs were not just useful for graphics, so we use them now to do many things like artificial intelligence, etc., because they're really good at calculating things in parallel, like matrix. But anyway, so it's interesting, right? Every time you see a big square painted in black, no, inside a PCB, you remember when we did unpacking intelligent machines, don't take for granted that's a computer, and nor that it's a digital, electronical, binary, general purpose computer. So the truth, but is that by standardizing our wall into this, by saying digital, electronic, binary, general purpose computer, we could say general or a specific, both coexist, let's you see. We basically standardize things a lot. And the truth is that the industry make that because it's a way to make things cheaper. And you'll find that if you open a machine, let's say a home appliance, let's think of a videotape recorder or a TV from 20 years ago, inside, it will look one way. If you compare it to, let's say, I don't know, like a radio work or a phone work, they will be completely different. One will have the things to move the tape, and one will have its own boards, its own connectors, and the telephone will have its own things, If you actually compare two devices that are kind of making the same, but are from our time, one will be the replacement of a videotape recorder. We could say maybe it's on a smart TV, right? Or one of those Chromcasts or things to stream things on the TV, That's what we use nowadays to play series, And on the other side, we put, for the telephone, we put a mobile phone, right? And we open them, they look completely the same. They basically have a processor, that runs some software, receive inputs, inputs for the TV streamer could be coming from the internet, right? And basically transform this into image and audio, And it does this inside a software that runs this. And if you look at your phone, that's the same, right? It connects to the network, you get your phone calls and your videos and whatever, and it puts them on a screen with audio and video. And so these two things actually will look the same. And basically the way we design things nowadays is like this, which I'm not saying it's good. It's just the way that the industry decided it was cheap, faster, and efficient for them to build things. So That's it. And I suggest you do it. Actually, one of the one of the things we do in MDEF, the unpacking intelligent machines, which is one activity we do at MDEF for the ones of App Academy about opening appliances and looking what's inside, is that usually if you look at the pictures, you'll see we open quite old machines which are maybe 15 years old, some. I do this because, of course, we open machines which are broken, and I try to that the appliances last. But also it's because the closer we go to nowadays, the more boring they are to unassemble, because they all look the same, and they just have one PCB with a big piece of silicon in the middle. That usually it's a general purpose computer with some specifics, maybe running a software that's we cannot access it many times, and that basically deals with those inputs and those outputs. No, so. It wasn't like this 25 years ago, and that's the power, or not the power, but it's the reality of living in a world which has been digitized and full of general purpose binary electronic computers. So we talk about digital versus analog, and I think Oscar will tell you more about this, so I don't want to extend too much. But you remember when I talk about the table, right? Or I talk about my voice, no? So just so you get a little bit more familiar with this idea, now the gray wave would be me talking and moving the air, right? The red bars will be how my computer will understand that. And you will say, oh, Guillem, but then actually when I am getting an audio file and making it digital, I'm losing a lot of quality, right? Because look, like I'll be missing it will be like that, right? It sounds super bad. No, actually, it's not true. It's not true because there's actually a theorem that defines how fast you need to sample something to actually be able to have an accurate representation. So what you see here, of course, is not the way it's done. Well, that might work well if actually we are trying to sample something that we don't care that much. For example, the audio when you talk on a phone, right? Doesn't need to be high quality. It's better, it's worse quality, so it weighs less and it's cheaper to send over the 2G, 4G network you are talking to. But if you think about audio, like a song, you'll like this to be higher. And so basically, this number of red lines that come up, no, will come higher. No, they basically will be more tied together. So we'll have, let's say, one. Instead of having, let's say, them separate like this, no, you'll have more of these lines. So let's say we have 13 lines here, you'll have 4 times those lines, no? And instead of having here 7 positions, no, on the X, you'll have, let's say 1,000 or 1,000,000, no? But still, when you zoom in, the gray line would never actually, no, there's always going to be an approximation, no? The point for us is to decide how much we want this approximation to be, no? And also to understand how we could actually make that approximation to be transformed back again into whatever our song was. So I don't want to talk more about digital analog. You'll get familiar with that, but it's just because you think that that's the way that we encode everything. And imagine the beauty, right? Because the beauty is, I encode something into digital, right? It's ones and zeros. If I have a general purpose computer and I encode something into ones and zeros, I can make my computer deal with any kind of information, right? And that's the beauty. We invented the internet for text. Then we started to share pictures. Then we started to share video. Now we're doing real-time applications in middle. We are doing Zooms. And the internet hasn't changed, right? It's ones and zeros. You can get a computer, let's say from the 90s, and you could actually, if you know how to do it, even open YouTube, right? No, it's not that we get a piece of hardware designed to run YouTube, no? And that's because when you have everything into ones and zeros, and you have a machine that's designed to process ones and zeros, depending on how you tell the machine to process ones and zeros, what we call the software, no? It means that we are really flexible on that. And that's the beauty, right? That's the beauty. Like, look, that's someone actually moving information, like with a horse, riding a horse, right? The Pony Express in the US, and actually like moving information physically, like with an envelope, And these people putting the poles for the telegraph lines, and information here you don't see it's moving, right? It just differences in voltage in wires using a primitive binary system called Morse code. And it's a primitive binary system. It just used two states, long and short, no? Or yes or no, no, depending in system. I think what maybe struggles us the most is to think how, okay, storing information into digital, it's fine, Guillem, I get you. Computing into a digital sounds hard, right? It's hard for me to get it sometimes. You know? It's like, okay, so you tell me that using ones and zeros, I can make multiplications, divisions, I could actually do all the fancy thing my computer does. And the answer I need to give you, it's yes, it's true. It's like that. And it's actually based on the fundamentals of what we call Boolean logic. So it basically means that at the end, the building blocks of a computer is what you actually see here. Basically, it's just a simple way of performing operations in the two only states our computer knows, yes or no. And by combining them, we could start to make things which are a little bit more complex. We could make things that count, for example, things that store one value over time, and I have a memory. So if I have something that counts and I have a memory, I could build a calculator. And growing on top of this is actually how we design a computer. And each of these and, or, etc., it's represented by different configurations of transistors. So at the end, it's quite beautiful. It's like the way you design a computer, it's mostly about arranging transistors in different configurations. It's not that actually, yeah, you might use some resistors and capacitors, but the fundamentals, it's about how you arrange transistors. Because transistors are designed, right, to do something when a voltage change. And so getting them actually to read these yes or no voltages, these ones and zeros, and combining between them, I could make things that count, I could make things that make multiplications, divisions. This, I don't want to extend too much because it's a long topic, but I'll show you some videos with the presentation. If someone is interested, there is a YouTube channel called Computer File, and there's super beautiful videos about people explaining how the things are put into practice. You'll see someone getting a breadboard and making a memory, just using transistors. And so you actually see that, you know, like the RAM memory in your computer is built with transistors, it's built with Boolean logic, and it could store a full YouTube video inside magically, but the basics are super simple. And that's something, if you love system design, which is also in the course of how we design these things, which is the fundamentals are still the same. You know, like the fundamentals of all this will be 100 years old soon. The thesis from Claude Shannon explaining that you could actually use relays to compute, I think it's from the 1930s. So let's say we've been building and building upon a system, and that's not bad, no? It's a practice that happens many times in engineering, no? It's like you design a system, you trust it, and then on top of that system, you start to grow it and grow it and grow it and grow it till you make crazy things with it. So we talk more about this after, but this is a way to get more into the topic of Fab Academy. We talk more about the software abstraction now, like what we talked till now. I mentioned silicon and transistors a couple of times, but I talk about binary, I talk about a specific versus general purpose. These things, it's like you could call, you know, someone calls you from a planet millions of kilometers away from the Earth and asks you, Guillem, here we have different minerals, we have, you know, like, and we want you to tell us how to build a computer, no? Well, I will tell them this, I explain you. And then they will figure out, depending on what kind of system they live in, no? The way they could make it. If they will use silicon, they will use, I don't know, a different approach. Maybe they use a different mineral. Maybe they don't even invent a transistor, invent something that works slightly different. But for us here on Earth, these ideas, we had to turn them into something physical, no? And let's talk about hardware. So that's how a computer looked in the 1940s. This is a computer actually running on valve. So the rounded things you'll see at the end, this kind of rounded shapes, those are valve. Those are valves that actually are kind of the fathers of transistors, okay? This is a computer already working with transistors. It's from an IBM machine, and all the gray parts you see are transistors now, and the ones that you see are resistors. And at this time, these computers were made around these kind of cards each card will do something. Like one card of those will be a counter. So every time it receives high-low, it receives 0 or 5 volts, for example, it might be capable of counting, no? So saying 1, 2, 3, and it will count these in binary. No, we'll count these by setting different registers high-low. This is actually the first computer that ever used integrated circuits. So we were at this scale, and this was perfect to build computers that were the size of that table or that room. So imagine 1950s, maybe you know this sentence, this quote from the IBM CEO that say, I think in the world there is space for about 5 computers. He thought, you know, like the US military, you know, the US Department of State, maybe, you know, like, I don't know, like the French government, the British government, and I don't know who else, you know, and that's all. So we are at this time here, okay? Maybe a little bit after 59, I think this quote is from 52, something like this, but anyway. So there was no need to make computers small. Suddenly, engineers had figured out there was a way to get something like this, no, into something that was much smaller, and that instead of having to make it by hand, you could make it fully automated. And that's how they come with integrated circuits, which we'll see in a moment what they are and how they work. But this new way of making circuits, it's the one that allows to build small computers. And this is the first small computer in a way that we built. It's the Apollo module guidance computer. It's a computer that actually, once they were in the moon and they were orbiting the moon, it helped the Eagle, which was the smallest spacecraft, to land on top of the moon. So it's a computer that's quite small for the time now. I saw it in pictures, something like this, okay? And it used integrated circuits. You'll see in a moment what they are. But it's just a way of making this much smaller, right? So each of those that will be like this suddenly was the size of this, was 1 per 1 centimeter, let's say, okay? So they built a system that instead of having, you know, 1,000 of those, had 1,000 of those, okay? But it doesn't mean it had 1,000 computers, no? All these chips together make a computer. In the early 70s, Intel built something that was truly revolutionary. They put a full computer into this. So this now is not a part of a computer. This now it's something that just, it's a counter or something that's a piece of memory that's stored. No, that's something that includes more or less a full computer inside. And that was the Intel 404, and it was designed to make a calculator because it was not yet powerful to make a full computer, but it was designed to make a calculator. And from this, having this idea of having not a full computer, but almost a full computer on a chip, it's what led to the revolution of personal computers. When you think about personal computers, you might, I don't know if you know, but the computer industry was a bit like the 3D printing industry 15 years ago, dominated by big industries that were just interested in a B2B model, selling to companies. And suddenly a bunch of geeks and freaks decided, I want to play with a computer. I don't care if it's not powerful enough to work. I just want to play with it. I just want to see what this does, no? It's like a bit like when you buy a 3D printer, you used to buy one 10 years ago. It's like you don't want to print anything, just want to see that and see actually how it works. So people like Steve Jobs and Wozniak, this is an Apple one, but many more people actually that even came before them. I just put this one because it's kind of a landmark. I started to get these kind of chips. I had to be more of other chips around and make personal computers. And these, you have to think that looks that size, no? But a computer at the time, not a personal computer, a mini computer, as they call them, was the size of a fridge. And a computer was the size of all those desks put together, no? So from this, which you had to assemble on a PCB, no? We went into like a lot of these first personal computers, like the Commodore 64, that all were based on this idea. We now know how to put a computer on a chip. So this is the computer. I'll need to add, you know, some memory. So these things here, okay. This means, sorry. It's not charging. I think this is. So, so it means, sorry, that one of these chips here, right, will be the computer, will be the one actually the processor, right? And then around you'll have the memory, you'll have the, let's say, all the graphics part, and all together will make a full computer, no? So from a processor to a computer. Then we went into this, right? And I think that's how you all get familiar with computers. I don't know what year you were born, but I was born in the late 80s, and computers that I got, let's say, for the first time, more or less, they look something like this. No, you'll go and buy a clone. No, you'll go and buy a PC that was built out of components made by different manufacturers, and that could run, could basically boot Windows. No, it was IBM PC compatible. No, and those were actually based in still in Intel chips, actually, like those one I show you mostly. Then on the 90s, also something started to happen. So when we were at this time, we didn't care about power consumption. We cared just about speed. We wanted computers to be fast, no? And you might remember, now we don't care that much about this, but 10 years ago, you were all like this, like, oh, I need a faster computer. My video renders take 2 days. They take just 2 hours, no, not 2 minutes. And so there was this rush for speed. But at the same time, actually, there was another trend coming, which was portable devices. And so actually on the 90s, a new familiar of, let's say, processors or ways of computing emerged, which was targeting more devices that they are not meant to consume that much of power, no? And this is this concept where they started to calculate the speed per watt, no? Which is not the speed alone, it's the speed per watt of power, no? It's how much electricity per computation, no? I put in there. Actually, who started that revolution, let's say, was a British company called ARM, ARM. And ARM basically started to work with Apple on the early 90s, building something that was called a Newton, which was kind of the first iPad. And then this company actually, this iPad was a complete failure, but this thing actually then went to these advancements they did in making computers or chips that could compute and consume less and less power. Actually, what like companies like Motorola, Nokia got interested into that to make mobile phones, and then digital cameras. You might remember all the revolution of digital picture cameras, on the early 2000s, and that's how actually these low power, high performance chips developed, and lead us to this, lead us to these kind of pocket computers. They don't have fans, they last on the battery for a few hours, and that's kind of the state, of this. Interesting, if you love kind of a bit the story of innovation, the people who actually designed those chips that they didn't consume that much power, ARM, did that not because someone asked them to do, did that because to make a chip that runs fast, you consume power, you need to cool, the chip gets warm, and so you need to make the chip in ceramics, which that's why big chips still, they're not white, but they're made out of metal. If you look like the processor on your laptop, might be made out of metal. And also chips which actually they don't need to be that fast, they are black, they are all made out of epoxy, And so these people actually, the ARM people, they couldn't afford to make the ceramic chips. So they actually had to, because it was too expensive. So they say, no, we'll make them in plastic, but we need to come out with something that's fast and doesn't get warm, so we could make it in plastic, And that's huge, is what triggered this, but it's just a comment. So this is what goes inside a phone like this, right? And that's the state of computing in 2010, which is 10 years ago. Now we could say we are more around this. That's a Raspberry Pi Zero. I think originally it cost $5. I don't know how, or £5. I don't know how much it costs now. And that's interesting because it's not just that this thing is cheap, is that it represents really well something that's really common nowadays. If you look on top of this, everything is green, and you just see one thing in black. And that's because that thing in black, it's not a computer. It's even more than a computer. It's what we call a system on a chip. The thing in black includes the processor, the memory, the RAM, the graphic driver, the audio driver, everything. It's inside a single piece of silicon. No, and that's the way they make the things, and that's actually the way that we think about chips nowadays. So that's the Fab ISP. It's something that Fab Academies for sure will build in a way or another. Sorry? You built one already, right? So if we look at the Fab ISP with what we learned, we have a PCB, and we got an integrated circuit, right, which is this black thing there, and that black thing is actually in a small computer in this case. If we look at this, for example, which is another chip, which is the one that runs most of the old Arduino, let's say, it's a Mega 328, and you'll say, okay, Guillem, you've been talking about chips, about silicon, but actually, what's here inside, no? Because the question is like, okay, yeah, funny, that's cool, but look, I get the point about you could compute like this, no? I get the point, I trust you when you talk about logic gates and these things, I'll search more. But actually, what's the point about this? So the point is that they found out that transistors were already made out of silicon. They finally found a way of, they call doping, of, let's say, changing the properties of silicon to make it semiconductor, and so to assemble, let's say, something that it's capable of controlling electricity without moving. So it's electronical, not electromechanical. So they actually said, okay, we found out that we could change the properties of silicon, not just to make a transistor, but to make a resistor, a capacitor, so to make actually all the components on a PCB, So they found out actually that you get everything here, more or less, everything on this green PCB, and actually make it on silicon. How do you make it on silicon? It's like you get, like you make a tiny ant to put these things together. No. Basically, they found out that using light, you could change the properties of silicon. So the way those chips are made is that you get a piece of silicon. Well, let's just think we're making a single one of those things. You get a piece of silicon, and you basically, imagine, you remember the slideshows? Or imagine you have a video projector. They project light on top, right, in different patterns, and those will actually define if a bit of silicon becomes a transistor, becomes a resistor, becomes a capacitor, and how it will connect with the others. So it's a process based on light. Sometimes when we listen like, oh, photonics is the future, and you say photonics, what do we use about photons? Well, all the computers around that you see, all your laptops, all your phones are based on a process which is strictly, let's say, tied to photonics, and actually even to physics, because keep in mind that you are working here at a level which is about atoms. So what you are designing actually is how to put atoms of silicon together using light. And then those atoms of silicon together will conduct electricity, will do things with electricity that will allow us to make a computer, or will allow us to compute on top of them. I think that's a more reasonable way of saying that. So keeping on hardware, I talked a bit about how the things are assembled, but what actually we need to compute, We said, let's say, how we build a general purpose digital computer. We know how to do the hardware. We know how to do this, We agree, we know how to do this. I mean, it's a process on light, on silicon. So at the end, those chips need to be designed. Like they design them first they design them by hand because there were no computers, like when this thing started in the 1960s. Now you design them with software and you design them actually by coding, Because let's say if you want to imagine, let's say you have millions of transistors inside a phone. You don't go and actually say, 1 transistor, 2 transistors. You basically write the script that says, I want to create a memory block of 16 gigabytes, So basically create a network of transistors to actually set this up, And the software, you write on code, And it will design this for you, And it will end up with kind of a projector, a slide, or an image. That's the one you'll use to actually create the different changes in silicon. So we know about this, but now let's think about, okay, this is let's say the hardware part. But now, what's the logic conceptually behind how a computer thinks? A general purpose computer, following more or less what's called as the von Neumann architecture, which was invented by von Neumann, which is one of the fathers of computers, and it's basically still, let's say, the way that most of the computers work is that you have three things. You have your data, you have your program, and you have something that computes. So what's data? Well, data could be anything that we could represent in ones and zeros. So for example, if it's a program that actually counts the number of words on a text, no? So data will be the words on a text. The program will be actually the instruction support to count words on a text. So the instructions I will say, a start, and want to find a white space, no? A stop, count one, continue. Want to find a white space, go back to that counter and add it to 2, no? And that way I count the words in the text. So that instructions will be the program, and the data will be the text. And the one that actually runs them will be the processor, with the central processing unit. We are making something different. We are making an Arduino. The data will be a button that we press. The program will read that state, will say the button is pressed, and basically the CPU, based on that program, will say, okay, if the button is pressed, then turn this output on. And the output on, which will be the LED, will be the data too. I'm saying that because when you think about data, it's not just about a Word file. Data are all the inputs and outputs too. No? Your keyboard is understood by the computer as data. Your screen is understood by your computer as data. Everything is data, it's information. And then we have other bits of information that are the program. Actually, think how cool this is, because you could make your CPU read a program, write data, and then decide that this data is a program. So you could actually make a computer that programs itself. No? So it's quite interesting, this concept, no? You could make a program that you say, look, if this situation happened, then basically change the program that bit and run that program, no? And that way, actually, data and program are actually quite tied together, no? Actually, if you think about your laptop, for your file system, Photoshop, it's the same like a JPEG file, no? Just ones and zeros are stored inside, no? The only thing is that it's true that your Photoshop doesn't reprogram itself, but it actually could do when it doesn't update, no? What does it do? It's kind of reprogram itself. So big computers had all these parts separated. So that's a computer on the 1960s. Had all these parts separated. So, like these, if we look at this, no? So one of these cabinets will be the CPU that process. One of those tapes there could be the data, no? And maybe some of these punch cards that this person there is introducing could be the code that will be run, the program, no? The issue is that nowadays we start to get things more tagged. So you look at a PC like this, like a proper big PC, we'll see things different. You'll see the CPU, you'll see the memory, and you'll see the program. So you could map it there. But it's true that nowadays, with integrated systems, it gets difficult even with your naked eye to see where the program is, where the CPU is. If we try actually to enhance a bit more that diagram, no? And we go to a more detailed implementation, no? That's the implementation you'll find in your microcontrollers, in your Arduinos, in the chips you'll learn how to program. So you'll have the program memory stores your Arduino code, no? The IOs will be the pins, inputs and outputs, no? To read LEDs, to control motors. The control, we'll talking about a moment about what it does. It's kind of the manager of the system. The arithmetic, actually, it's the one that will perform the most mathematical operations, can compare two numbers, can add two numbers, can do things like that. And the data memory will be, in a way, our playground. So think of it in a way that you got the program on how to do something now, and this program might tell you, okay, go and read digital pin 1. You'll go to the I/O, no? So the control will start, no? We'll go into the program memory, we'll fetch the instruction, which is read the pin, and we'll go to the I/O, and we'll execute that function, no? The result of that function, if it's on or off, no? Let's say, we're reading a button here, no? So program memory, read the button, control memory. Okay, I go to the I/Os, I read the button is on. Where do I store this on? Into the data memory. Second instruction on the program memory. If it's on, then trigger output 2. So control reads the second instruction. It says if it's on, trigger output 2. Okay, it goes to data memory. It checks back what's stored before. It sees that actually was on, and it writes back into the I/O those. No? In here, we are not using the arithmetic memory. The arithmetic will use it maybe a little bit more if we actually start to, for example, count things. Actually, in a way, we could say we are using it because we were comparing, right? If we actually stored in data memory, the button was pressed with a 1, let's say, no? And now we have to compare it if actually it says this program, if it's 1 to something, so we'll do it there. I don't want you to fully get that, but just to get a bit the grasp of how these things are implemented. And keep in mind that that's just one architecture. There's different architectures. There's not a limited way of making this. So that's what goes inside an Arduino. And in an Arduino, in any of those boards, we actually talk about microcontrollers and not computers or not processors or not microprocessors, just because it's the word we used to say that inside this black piece, there's everything. There's the program memory, there's the data memory, there's the control, the arithmetic, and the I/O. Everything inside a single physical piece. When if you look at a computer that just runs on a processor, a standard microprocessor, you'll see something more like this, where there's a processor, there's the memory, there's different parts. In an Arduino, everything is inside a single microcontroller, no? Because it has that, basically they design a piece of silicon that includes everything. The hard drive, the RAM memory, the processor, everything inside, no? A single piece. This is a chip on an old Arduino Uno. And actually that's the only thing this needs to run. You'll learn more with Oscar. Moving forward, I want to finish soon. So we talk about here about the hardware, no? And the architecture. So I will like you to start seeing that these things are not magic. The first bit that we need to check is the software. So that's an Arduino, right? That's a Raspberry Pi. No? There's one big difference between them. It's actually not fully true, but it's good to learn and to get as an example. So when we have a processor that's quite small, and to tell you what's quite small, maybe check this table. An Arduino, it's 16 megahertz, right? A Raspberry Pi, not the newest one, maybe the Raspberry Pi 2 or 3, 2, I think. It's 700 megahertz per 2 cores. No? If you look at the memory, it's 2Ks versus 512 megabytes. So it's 512 plus 6 zeros behind. And the other one, it's just 3 zeros, no? So it's magnitudes of a scale different, no? So, and look, for fun, you could check the Apollo computer, how small this is, no? And it actually landed something on the moon. So when you get hardware, which is fast enough to do what you want to do, you could start to make your code to be easier to use. And that's what an operating system does. So Arduino is so small that the only thing we could ask him to do is, okay, I put the instructions that exactly do what I want to do, which is read that pin, calculate something, trigger that pin out, and do this in less than this time. Because imagine, you'll say, well, time carries a lot. You are moving the motors on a 3D printer. Imagine something takes more time than expected. Instead of making a circle, you might make an oval, no? Because that motor might be moving slower than this one, no? So time is super important, especially in this kind of chips and Arduinos and things that control things that move. When you get actually something that's more powerful, like your computer, like your phone, you could start to do something which is pretty cool. It's to add software that takes care of things, so you have to write less code in a way. And that's what the OS does, right? Your operating system, Windows, Mac OS, Linux, it's software that runs on top of your hardware and abstracts many of the functionalities of the hardware. So for example, when you want to save a file on an Arduino, you actually will need to control everything. First, you need to know to whom you talk. I'm connecting an SD card on my Arduino, so I need to know the SD card. There's a protocol called SPI, and I'll need to bing bang all these pins, high, low, high, low, high, low, and I'll need to think, how do I encode the information? If I want to store a picture, how I do it? I just start with the pixels it has 1000 per 800, then I will start all the colors, ones after the others, no? If it comes a second picture, where I will put it after this in memory. How many remaining memory I have, how many files I have, what happens if I want to delete, what do I know where a picture was versus another, no? All the things in a normal computer are not managed by your program. Photoshop doesn't need to take care of these details. DOS, Windows, Mac OS abstracts the system for him and tells him, oh, Photoshop, I see you're asking me to save a picture. Okay, don't worry, I'll take care of it. Where do you want to store it? It presents a dialog with interface with your USB drive, your hard drive, all the things, no? And that's what the OS does. It's a level of abstraction written in software that abstracts all these things. From abstracting the hardware, and that's super nice because it means that you could get an OS that runs like Windows. It's amazing on that. You could get it running many different hardware, no? And always works well. Well, but I mean, it's so basically that's the power of an OS. But in what you learn to code these days, usually we don't use an OS. You could put an operating system on the Arduino. Eh? There's operating systems that's small enough to fit there. There's one called RTOS, one called ChibiOS, and you could put them on the Arduino, and they simplify things, I promise you. But they're also complex to learn at the beginning. But they allow an Arduino, for example, to say, please, trigger this function in 10 minutes, and it does it for you. You don't have to go, if time equals that, do the other, check it. No, it does all the things for you. So that's important to understand why in Arduino we don't have an OS, no, usually. In Arduino, in many systems like this, which are super small. But step by step, it's true that having an OS is getting more common and more common. Why? Because remember what we said at the beginning. When you get hardware which is fast enough, no, you could put an OS on top. Hardware gets, let's say, faster every year, so it's making sense for us to put an operating system inside. And even small systems nowadays might run an operating system, like in a small Linux, they might not run Mac OS or Windows, but they might run something that you could make small. Well, the last bit, it's about compiling, because we talk about the architecture, the software, but let's look at the last bit, because that one that confuses a lot, programming languages and tool change. So, well, first of all, let me see, let's say, let's say programming languages that you might know. You maybe know, if I say Python, you might know what it is, right? Maybe if I say, I don't know, C++, maybe it resonates, JavaScript, I don't know, like Grasshopper. Some people maybe, I don't know, if you like more from the visual scene, you maybe know Touch Designer or VV, or maybe you are more from the, I don't know, hardcore simulation, you might know Fortran, or you might know C# because you come from the Windows world, or you might know, I don't know, Ruby, or, so all these are programming languages, right? And there's this kind of cool thing always, it's a bit like the MyPC thing, you know, I prefer Python than PHP. It's, you know, there's always these things. Well, we invent languages like we invent, you know, like tools. It's like there's designers, and there's that, and you came with a nice paradigm that you love, you know. Someone says, no, the best house is the one that has 2 stories because you sleep in one, no, and you spend the day of in another. So someone says, no, the best programming language is one that favors expression of your ideas. No, the best language is one that favors speed. The best language is one that is able to run in many different systems. But all these are conventions. I mean, people design them, like you design a hammer, you know, and you say, look, I need a piece of wood because wood is good, because if I have my hand squared, it's something that might stay properly into my hand. I need a piece of steel, you need to have a certain weight, a certain diameter, because if it's like this, no? So you design something, you design a language. So languages are designed, no? They say that if you type and you say if, and you open, let's say, brackets, it's because I'm saying, okay, it's maybe good to put the word if, which is an English word for saying, a comparison, and then actually opening brackets. But you can say, no, I prefer to be different. If will be, I don't know, another abstraction will be letter A, or will be a dot in colors because my language is visual and I use dots in colors to represent an if. That's completely up to the designer of a language. The truth is that always, in a way or another, this language is turned into instructions that the machine understands. So this, it's a sum of two numbers in an abstract language. Actually, in Python, in C++, in C, in Java, I would say in many languages, a sum, it's written like this, Even at our natural language, usually at school we learn how to express it in mathematical language like this. What the computer does when it does this, well, you'll get this piece of code. Let's say it's C++, Python, JavaScript, whatever it is. And then your computer, in a way or another, will learn about, it will turn it into something that looks like this. Not exactly like this. Like your phone running an ARM processor might have different ways of doing that. Your Intel chip might have different ways of doing that. Even you could tell the compiler, which we'll learn more what it is, to make it specifically in different ways. So we are flexible to range that and achieve the same functionality. And that's why actually you need to compile something for to run in a phone and something to run in a laptop, sorry, in a laptop, yes, in a PC. So you get in here, Let's imagine you want to sum, that's my code, okay? My code here, and say sum number 1 to number 2. Well, first thing it will do is that it will turn this into machine code. And the machine code are the few instructions that our computer actually knows how to do, that these transistors know how to do based on the different arrangements they have. So this thing here, it's based on the way Intel chips work. So these instructions that say LDR might change depending on the architecture, but so you get familiar. Load, so what I will do is first it will get number 1. Let's imagine that number 1 is 2, And it will load it into the register 0, which is a part of the memory. You remember when we talk about program memory and data memory? So the control part will basically check this, but it won't find this. It will find this. Because you compile the code, it's inside your program memory. And it will basically get this number and put it into the register 0, which is kind of a box in the memory, which is called R0. It will get the number 2 and will do the same, R1. Then it will run another instruction called at, which means in box number 5, basically put the result of adding R0 value plus R1 value, That's this part here. And then finally, get what's on R5 and turn it into the sum, which is the result I said here. So that's what internally happens in your computer. Why? Because making a computer that understands natively, making transistors to deal directly with the C language will be quite complex to do. Rather, understanding, let's say, 100 functions, it's easier. Because keep in mind, for each of these functions, there's a group of transistors which needs to understand them, So let's say it's quite complex to make transistors understand everything in a way. So you basically make this in software, and then in the hardware, you just understand a few functions. Well, that's kind of a complex topic, so I don't want to extend too much. I just want to tell you, and we finish because it's almost 1:30, that when we talk about an Arduino, for example, because you'll use Arduino those days, we are not talking about a particular board or a particular chip. We are talking just about the combination of two things, what technically we call an IDE, an integrated development environment, which is a place where we could write code and compile it into machine code, and a particular chip or family of chips that we support. And Arduino on that, it's nice because the community created support for many, so you could write code in actually in C++, staying on the Arduino IDE, and when you press the button, it will run what's called the tool chain, and it will be able to compile that code into any microcontroller, any board that you select. No? And that magic, it's what this combination of hardware and software is what we call Arduino. No? This integration that makes it easier for us to work. It's not the only one. There's hundreds of solutions similar to Arduino, more targeted to the industry to do that. No? Actually, and as a way to finish, what happens when you compile code? So when you compile code and you compile code into the Arduino, some of you might be already a bit familiar because you use it in some projects. I say Arduino, keep in mind, ESP8266, Note MCU, ESP32s, even when you compile code in C and a Raspberry Pi, not even using Arduino. So what the Arduino does is that it gets whatever code you write there, like, digital write, pin 13 high, and then delay, 1,000 milliseconds. No, you might maybe be a bit familiar with this if you ever open an Arduino example. So what we do there is that we get that piece of code and we load on top of it what we call a library called Arduino.h. A library is a set of instructions that will allow C to understand that the digital write is something, because C++ doesn't have a function that's called digital write. That's an Arduino function. So we'll load a set of resources that say, look, when you find a digital write, we mean that for you. We mean to write these instructions. We can go this more in detail in another class. It gets all these things, okay, and it uses a tool called GCC. And GCC, it's the tool that's capable of getting the C++ code and transform it into machine code that will look something more like this here, okay? Imagine how important GCC is. That you might know about the Linux project, and the Linux operating system. The Linux operating system, they're gonna start building an OS. The system, as you might know, it's called New Linux, GNU Linux. So the new project, the first thing they had to do was to create a compiler that was free. So they could actually compile the code to make the OS. So the compiler is like, it's interesting that, it's like at the time, there were compilers for C, but you had to pay to use them. And what they were running inside, it's something that actually you didn't know about this. They wanted to create a free, open source compiler, so something that could transform C code into actionable code, into code that you could run on a computer. And they start building this. After building this, which was called GCC, it's the open source new compiler, they actually were able to write Linux, So it's interesting, And actually the compiler, if you think in a way, connects well with this thing here, in a way, because look, we get a program to write another program, isn't it? The compiler is a program that's actually capable of getting this, which is actually another program, and turn it into another program, So it's kind of, we create software to create other software, And at the end, it's about this idea of levels of abstraction, that we always deal in computing. It's like computer scientists love onions, I always say, Levels of abstraction, And you keep adding levels of abstraction and levels of abstractions till you could do things, let's say, which are so far away from the atoms that move inside your laptop that you don't even believe that they are, And that's this kind of magic effect. We always go, whoa, where it is, So finally, the last bit for you to get, and promise you it's super fast, is that when you get something like this, you need to run it. If I compile this and I want to run it in my computer, it's easy, It's there, I say my operating system, go and run that file, which usually it's as simple as clicking on top of it, You click and it runs that file, Well, if I compile that code in my computer, but I want to put it into an Arduino, first I need to compile it for the Arduino. So these instructions here might change, might not be LDR, might be a different kind of instruction set. But after I need to put it into the Arduino, It's like I compile in my PC, I now want to put the code into my Arduino. In fact, technically that's called, if you want to search about it, cross-compilation, I compile in one machine, but I put the software to run in another. It's not the same architecture. No, it's not like I compile on a Mac and put on a Mac. I compile on a Mac, but I target that I want to build something for an embedded system like an Arduino, for example. No? So the Arduino, there's many versions, but actually what we need is something that's called flashing. The action of flashing means basically getting the result of my compilation that in here it's written nicely, but this will be then turned into just ones and zeros, no? I need to put it inside the memory for it to start. And the way I do this is that usually on the boards, I run inside something called a bootloader. A bootloader, it's another piece of software running inside my board that actually it's expecting to receive new code, in many cases over the USB connector. And once it receives code over USB connector, it will get all this code, which actually are all these instructions here, no? And it will get this code, and it will basically set the transistors inside the memory in the correct positions, no? So the next time I boot and I finish, actually it runs a bit of code, no? These you might say, oh yeah, Guillem, that's super complex in an Arduino. And how my PC does it? Well, your PC does the same. Imagine, you start this, no? You boot your computer. And when you boot your computer, it's just a bunch of transistors there, right? So there needs to be something that says, look, wait. I'm on. I need to see if I have a hard drive connected. If I have a hard drive connected, then I'll check if this hard drive is actually actionable. If it's actionable, I will get all the switches inside the hard drive, the ones and zeros, to say it in a way, and I will start to load them into memory. And once I get these things loaded, I'll be able to talk with maybe the other peripherals like the USB, et cetera. And if this works well, I'll go and get more code and load it. No? And that's actually how your computer boots. No, actually, usually the computers, they boot in stages. Your Mac boots and boots kind of a mini version of Mac OS, no? That just allows him to check it's fine. And if this is okay, then it goes and fetches more code and boots the full. So this concept of things that help machines start, that we call bootloaders, it's super common. And flashing, it's a word we use more for microcontrollers, but still it happens in your computer. We don't call it flashing, we call it just updating the hard drive, or the OS, sorry, not the hard drive. But I mean, so you see that these concepts you learn these days from flashing, compiling, architecture, software, are common across all the digital general purpose computers that you live surrounded with. And I promise you there's tons of them, and you'll find them everywhere, not just in your laptop or in your server or in your Raspberry Pi. Everywhere you'll find computers, and they all are programmed the same way, okay? So once you learn about these things, you're done. I mean, of course you're not done, but I mean, you know the fundamentals. You know that, and I don't think it will change anytime soon. We'll have to wait for quantum computers to be there, and for sure, as people like abstraction, someone will find a way to code them in a similar way, because as you found out, we like to put layers of abstraction on top of things. So I would say even with quantum computers, maybe we end up having similar tool chain just for the convenience of the industry, that we found out that, they like standardization, so they could make things cheap and efficient. So this is a bit, let me know.
That slide with all those switches that were on and off with the lights. So
wait.
The question was how transistors store information when, say, your computer's off. So you don't have any current going through them, they're going to stay in one position. Let's call it A or B, and it's going to be 0.
So depending on the kind of configuration, the standard configuration for storing a 1 or a 0, it's what we call volatile. So it requires electricity to be fit in. That you run memory, the one that stores the position of my mouse now when it's moving. This is volatile, and so it needs power. Before we didn't know how to actually make transistors store information when they were not power. And that's why for many years, the only way to store information without power was to actually store them mostly as a light on a CD, for example. No, a CD basically has the scratches on the surface magnetically, like a tape, like open reel, like the floppy disk, and like the hard drive, that we all got since a few months, let's say, or years, where storing information into magnetic, no, like with a magnet, no, like magnetic, no magnetic, magnetic, no magnetic, no magnetic is a 0, magnetic is a 1, you encode information. What they found out actually is that they could, as we said, that with this process of changing the property of silicon, it's not just about making actually transistors. I could make capacitors, resistors. So you could take the properties of a capacitor, which allows to store energy in the forms of a static electricity, and use that to design a memory component that it's capable of storing electricity even when it's not power. But it's an interesting question, the one you had, because actually the memory, if you think about your memory and your drive, let's say in your Mac, you might think that actually it's something like this, and that each of these switches represents a 1 or a 0, and that directly represents maybe your OS like this. But it's actually not true. There might be 1s and 0s of those which are redundant. And there's a lot of work happening. So actually you could read those 1s and 0s properly. So for example, as the memory knows that if it's always storing the information on the first switches, it will burn those switches. No, it's like at home when you have the classical switch that everyone is pressing all the time. It's the first one that breaks, and maybe you have one in a small room that you just go once a week, and it lasts for many more years. So to prevent those things, your memory, or your hard drive, it's doing all sorts of crazy things. Like for example, saying every time you ask me to store something, I'll put it somewhere else to distribute. No, so there's all sort of things that we take for granted that are happening behind to actually make this physical system, because it's about beads and atoms, no, that move inside, and it's physical. There's atoms moving inside. Be so seamless, you know. Yeah. So yeah, this is. I hope this helped you. Any comments, questions? Oscar now will unfold completely the wall of how you make this happen. No, but I hope this did help you. And in case someone is interested, I'll share you then a bunch of videos. You don't need to watch them, but if any time, oh, okay, what is it about? You go there and check them. But I think you are too busy now to actually look into many of those, I think. But it's good to keep them in mind, because sometimes if you don't get the fundamentals of these things, you can get quickly confused. You can end up thinking that, I don't know, that Python is magic and C++ it's not, or that macOS and Windows are completely two different things, or that Arduinos and laptops are not the same. No? And I think it's good not to be confused. But we can. So this is, I think now we might take a break, and it's time for Oscar to jump into Arduino.
Yeah.
Super.
So let's take, what do you think, 10, 15 minutes break? Today we will finish at 1 because they already changed the for daylight savings in the States, and the Niels class is at 2 today. There's 2 weeks that Niels class is at 2, not at 3. So we finish at 1. Okay. Try to be here around 10 to or 5 to, and we do 1 hour and we are done for today. Okay.
Oh,